Data Modeling and Best Practices. My name's David Pearson with Amazon, and I'll be introducing Peter Mark Burwood very shortly, who's one of our solution architect and design experts. I just wanted to start off briefly with a little intro to databases in the cloud and how we conceive of these the data tier in the cloud, because it's evolved significantly with the advent of the cloud and the ability to bring effectively unlimited resources to the data tier. So if we look at the first slide, Peter Mark, can you just forward that? Thanks. The traditional database architecture has always been client, app, web tier, and then relational database. And if we look at how the relational database is used on the next slide, it's really as the Swiss Army knife for all sorts of workloads. Key value, complex queries, transactions, analytics. And, the default has been, let's use relational. And that's been great until the advent of big data and specialization has overtaken these sort of requirements. And so if we move forward one phase into the next slide, we'll see that the way we approach the data tier in a cloud world is really to talk about specialized approaches to managing data. And more specifically, the specializations that have emerged, you can see them there: NoSQL, relational, data warehouse. And these haven't necessarily come about as a result of the cloud. Warehousing, specialized warehouses have been around for a couple of decades now. It's more to the point that now the cloud enables these to be super agile and allows people to manage what would otherwise have been a complex array of different types of data store, do that really efficiently. In other words, specialization doesn't cost you an administrative nightmare. So if we roll forward, really the idea of this is really to say, on the next slide, the workload drives the data store selection. So it's simpler queries of very high scale in a NoSQL environment, and that's obviously the thing we're going to focus on today. Rich search, transaction processing, really the core of relational databases value are leveraging those relations for very rich queries. Obviously, caching for hot reads, logging in a blob store, just an object store in the cloud where you just put data, stage it there, unstructured, and access it later. And of course, a warehouse for analytics, SQL-based, but inherently architected for high performance in terms of scans. So if we roll forward, we map these tiers, these options in the cloud to specific services in AWS. And these are the data tier services that we provide, from cloud search to S3. People are very familiar with S3 by and large. The ones in blue are those that fall in our category, what we describe as database services, which is essentially cloud-based structured data stores. So we're going to focus on DynamoDB today, and if we roll forward, I'm going to introduce Peter Mark and allow him to take us through into much more detail on exactly how you design for a NoSQL-based store in the cloud, specifically around DynamoDB, but really best practices being best practices. This can apply anywhere. So Peter Mark.
Thank you, David. So as David said, my name is Peter Mark Verwoerd. I'm a solutions architect for Amazon Web Services based out of New York City. And what I'd like to do today is go over a few best practices on using DynamoDB and how to data model various ways of using different kinds of data state in DynamoDB. And what we're going to do is use gaming as an example. While we're using gaming as an example, I think it's important to note that these best practices can really be generally applied in a lot of different situations. So it's not to say that this is really only using for gaming, but rather they have a rather broad applicability. And so what we're going to do is we're going to walk through these 6 different modules, these 6 different design patterns, and look at a particular feature of DynamoDB and see how it applies in use cases that we're going to go over. And one thing that we think is important is that we're not actually going to talk about the feature and then see how you would use it inside that design pattern, but rather we're going to talk about real-world examples and see how DynamoDB helps model particular behaviors or solves particular problems using the data model. And so it's really important for us to see how it works in practice rather than at the theoretical level. One last note I'd like to say is that each of these 6 sections, they build on each other to a certain extent, but what we're going to do is have questions at the end of each one of these modules. So if you have questions, we're going to pause at the end of each of these 6 in case you have any questions for us. Let's move right along. So the first thing we're going to talk about is maintaining a basic game state, and we're going to do that with conditional rights. So let's walk through our very simple game, and we're going to use tic-tac-toe as a model. I'm sure you're all familiar with the gameplay. And so setting the situation, we have two players. We're going to call them Alice and Bob. They're going to be making some sort of communication to an application that's been written that's going to process the game, and we're going to be saving our game state on DynamoDB. So let's look at what that looks like when we save it. We've got a DynamoDB table and some data here, and we're going to look into what exactly this data is and what it shows right here. So overall, we have a DynamoDB table, and when you create resources with a DynamoDB service, that's what you're creating. You're creating a table. So the concept of a database itself does not exist in DynamoDB. It's just tables that you create, one or more, however many you need. Within that table, you have any number of items. So from a relational database world, this would be loosely equivalent to a row. But in DynamoDB, this is an item. Items are made up of one or more attributes. And again, this is coming from a relational database world. This is loosely equivalent to a column, although you can already see one difference is that this column here is not populated by every row. It's only the top row has this column. And this is perfectly allowable in DynamoDB. Attributes don't have to exist across different items. You can have however many different attributes. You can have no attributes in common at all if you wish, and that's perfectly allowable in DynamoDB. In some circumstances that's useful, in other circumstances not so much. The only thing that you absolutely have to have on everyone is the primary key. So in this case, we've got a randomly generated string primary key for identifying each game that the players are playing. And this is the only one that's required. This is the only attribute that's required across all items. And finally, if we look at some of the data types that we have, you can see that the players are being stored in a set, a string set, which is an unordered, unique group of strings. We also have strings for state, strings for the who's the host. We use number for a tie to represent a Boolean. And actually, finally, to represent the actual game state, the state of the game board, we're using a binary data type. And what that looks like is a very simple representation, a text representation of what the board looks like. So if it looks like this game's done, and whoever played circle had won this game. So back to the game. We have Alice and Bob, and they're going to make a series of moves, and we're going to store the data in DynamoDB. So let's start the game, and we're going to start with Alice playing first. So Alice is going to make a move, and she's going to update the state of the game. And so instead of writing a new item to the DynamoDB table, she's going to update the existing game item. And she's just going to say, this is my move, and now it's Bob's turn. So Bob is going to do the same thing. He's going to pick a location. He's going to say top left is now X, and it's Alice's turn. If you know anything about tic-tac-toe theory, this means that if Alice were to go in the bottom left corner, she could win. So this is really not a good move by Bob, and Bob realizes this, but instead of trying to play better, he's going to try to find out a different way to win. So what he's going to do is basically cheat. He's going to submit 3 moves at once. He's going to say, well, I'm going to take the top left, the middle, and the bottom right. And he's going to write all 3 of those to Dynamo at the same time via the application. And then what's going to end up happening is the state will change to a Bob win. Or maybe it'll crash the logic of the application, something or other. One way or the other, Bob's not losing. So he's happy. So let's take a look at what this actually looks like in terms of what we're updating on the item. So if the item right now says that the state has been started, it's Bob's turn, and only the top right has been claimed by circle, what happens when Bob submits 3 updates changing the state? So each of these updates say the turn should go to Alice, and we're going to put an X in various locations, in the top left, middle, and bottom right. If we then submit those updates to DynamoDB, DynamoDB will happily accept all of these as updates. All an update does is change the state of a particular item that already exists and updates the attributes specified. So we're changing turn from Bob to Alice. Whichever one of these updates comes in first will change the turn to Alice from Bob. But the other 2 that come in are simply changing Alice to Alice. And then the top left, the middle, and the lower right don't conflict with each other. So there's no reason why all 3 of those updates won't be accepted. And so just the way that we've constructed our API at the moment, there's nothing that says Bob can't do this. So what we want to do is inject some sort of logic in some sort of way to prevent Bob basically from cheating. So we've got to fix this. And we're going to fix this using conditional writes. And the idea behind a conditional write is that you can make a write to DynamoDB with including information that you expect to be there. And if that expected information exists on that item already, or if the expected state of that item is what you're predicting, then the write will be accepted. If that state is not what you're saying is expected, then the write will be rejected. So let's take a look at what this is in our tic-tac-toe game. So now we have the same state. We've got Alice and Bob as players. Game has started. It's Bob's turn. The top right has been taken by circle. Now let's see what happens when Bob makes his update to claim top left as X. What he's also going to do, what is going to be part of that call, is that it's got to be his turn. The top left can't be taken, and it has to have been started. So you can't update a finished game or a game that hasn't started yet, and you can't write over a location that's already been taken. So let's try and see what happens if he tries all three of these. He's going to make the same updates that he did before, the top left, middle, and lower right, but he's expecting always it's got to be my turn, and always that location has got to be available. So if he tries to make those writes, what's going to happen is Dynamo is going to receive one of them first. It's going to serialize each one that comes in, and so they're going to be processed in a certain order. Whether it's 1, 2, or 3, it doesn't matter. One of them is going to come in first. So let's say, just for the sake of example, that first one, the top left, is the first one to come in. What's going to happen is it's immediately going to change the turn from Bob to Alice. It's going to claim the top left. So that means that when the second and third API calls come in, they're going to fail because the condition has been changed from Bob to Alice. And so the expected condition is going to fail. It's no longer Bob's turn for 2 and 3. And so they're just not going to be accepted. The middle and the lower right were null, but that doesn't matter because part of the expected portion of the update was not correct. So they're just going to reject those writes. And so this way we're building a game such that Bob can't cheat. So we've got a functioning kind of normal back and forth sort of game. So any questions on that portion?
Hey, Peter Mark. Yes, we have a couple of questions. Can you talk about the latency of DynamoDB relative to, say, a typical MySQL database and even Redshift?
Sure. So DynamoDB was built, there were a number of requirements, but I think some of the obvious ones were clearly it was built to be low administrative overhead. When I said when you get started you create a table, really that's all you need to get started with DynamoDB. The other thing that was a big requirement ahead of time was that it needed to be fast. We really wanted to have very low latencies when using DynamoDB. So actually the entire storage system is built on top of SSDs. And the latency of the system, generally speaking, for reads is under 5 milliseconds, and for writes is under 10 milliseconds. So that's relatively consistent across the board for DynamoDB, no matter the size of the reads and the writes and the size of the data set that you're dealing with. And also the amount of transactions that you put through. DynamoDB is very, very consistent in that regard. Compared to something like MySQL and Redshift, I think for MySQL and other relational databases, it's going to depend quite a bit more on the type of hardware that you're running and the type of workloads that you're running. So longer queries or bigger queries are going to have lower latencies, or longer latencies, I should say, greater latencies. And of course, the hardware that they're running on, or the virtual machines that they're running on, the larger the machine type, the more memory it has, the faster the disk it has, it's all going to affect the latency. So there's a pretty big range of latencies that you could get out of a relational database. Meanwhile, Redshift, there's more consistency in the hardware where there's a fewer range of hardware types, or virtual machine types, I should say. But still, the goal of Redshift, I think, is significantly different from DynamoDB, whereas a data warehouse is not built for the immediacy of, say, a transaction. And so the latencies are probably going to be quite a bit longer, even for smaller queries. So I think while we're talking about milliseconds or in the order of milliseconds for DynamoDB, Redshift operates more in the seconds territory.
Great. Yeah, and I think that specialized work, a data store for different workloads is the key there. Analytical workloads on Redshift usually have a scan requirement. In other words, how quickly can you scan a billion rows as opposed to how quickly can you return one row, which the second one is really a factor of latency. So question on overwriting. In the case you were talking about, how do you overwrite? What happens if you try to overwrite an existing item? Basically an update. How does that work compared to an insert?
An update is writing to an existing item, an item that's already been there, and as long as that item is valid, as long as the write that you're creating is valid, it's going to go through. So you can overwrite portions of an item. So if you only want to update certain attributes, like in our case, we want to only update the turn and part of the data that's holding the state of the game. We don't want to update the participants. We don't want to update the ID or anything like that. We're just updating a portion. So that's the difference of that's what an update is doing. And if it's without conditions, it'll go through as long as that item's there. If you want to create a new item, then that's more of an insert. So the difference is the update just happens kind of seamlessly as long as it's well formed. If it's conditional, it'll happen as long as that condition exists and is valid. If the condition is wrong in some way, then the write is just not accepted.
Great, thanks. And just on conditional writes, how easy is that to add to a statement? What does that kind of look like just in terms of the complexity of code?
I think the complexity is related to the complexity of the data. So it's not terribly difficult given our SDKs or even the direct API. It's very much built into that statement, that update statement, and so it's written in such a way that we almost expect it to be there, or if you use it, it's not going to be onerous to include. But how complex that is going to depend on the logic of the application and the needs of that application to what way are you manipulating the data and what way are you expecting that data. So the complexity is kind of directly proportional to the complexity of the logic, but actual implementation is not significantly different than writing a regular update.
Great, thanks. Okay, we've got some more questions, but we'll try to get to them at the end, and we'll keep moving forward. So next section, thank you.
Thank you. So our next section, we're going to talk about saved games. And so while we have a valid game state that works and prevents Bob from cheating, what we want to do now is actually save the state and be able to replay the game, which is a fairly common scenario where you can envision, whether it's a game or anything else, where we want to save what we've done and be able to look at what we've done previously. So if we're looking at tic-tac-toe, what we're doing now, we're not just saving the current state. We want to be able to save each point of the game where we can replay what happened, either to judge how things went, to be able to learn from mistakes, to be able to use machine learning to process what different decisions were made, or maybe even go over certain aspects of the game, looking over end game or looking over opening moves. So how would we model this in Dynamo? If we look at our existing data model, this isn't going to help us. What we have right now is just a hash key for our primary key. And while this is useful for our first use case, this is not going to help us on our second use case. A hash key basically only gives us a key value store. And in our case, we want to really do queries. We want to query across our information. We can't really do that unless we know the specific ID of the game. And even if we have the ID of the game, we can't figure out how things happen, in what order things happen. So we need to add some more data. We need to change our model slightly. So what we're going to do is use a hash and range key schema. So with a hash and range key, you're still creating a primary key, but they're creating a primary key together, which means that the hash key doesn't have to be unique as long as a hash and range key combination are unique. And in this case, now what we can do is add a turn concept to each data entry. And so now what we can do is actually replay what happened over the course of the game. We can check out what happened at each step, what the game state was at each step, when was the game done, when it started, who won the game, and so on. So with a range key, what you can do is actually start to query within a hash key. And so within this hash key, this game ID ABECD, we can now make queries on our range key. So within that hash key, we're going to order the data by the range key. So we're going to order from 0 through 4 in this case. But now we can make queries against that. So just to go through a bit of the differences, a hash key schema, a hash key table, basically gives you only a key value store, which useful for some use cases, not so much for others. It really depends on what your data needs. Hash and range key is given a range key, you're going to have a queryable index, and that's going to be the range key. And like I said, the items are sorted by that range key within the hash. And so let's say we're going back to our table now. Let's say we wanted to see what are the last 2 moves of a game. With this schema, we can actually do that. And so we can say, let's just look at what happened the last 2 things people did, or how do people open. If we wanted to analyze that over hundreds or thousands of games, we could get the first 2 moves. And so with the query API call, you can do things like you can order it by, you can do ascending or descending, you can limit how many, you can say less than, greater than, in between, and for strings you can actually do starts with as well, which leads to some other interesting queries you could do. Any questions on that section?
So just a couple of things. I think we're back to the conditional write a little bit. If we do a conditional write that fails, does that consume read provisioned? In other words, provisioned I/O, write provisioned, or both? How does it compare if I'd done a read then an update?
Well, if you've done a read and then an update, that's going to consume an appropriate amount of read capacity and then write capacity. If the conditional write fails, then you're not consuming any writes.
Great. And how many attributes can be included in a hash range?
The hash range, so a hash and a range key individually are single attributes. And so a hash key, while being the primary key, is also itself an attribute. And a range key, while being, again, an index essentially on that hash key, is itself an attribute as well. So they're each individually one attribute.
Great. One more question we'll field. So in the tic-tac-toe example, it was described that the data was a single field. So presumably that means attribute in our terminology. Is it possible to just update an attribute, or is it the entire item that needs to be updated when making changes?
It's absolutely possible to update just a single attribute. And I think some of the examples that we walked through simplified the data of the game state a little bit, where we had that rather larger view of what the actual game board looked like at a given moment. While when we're going through the updates, we're just updating, say, top left to X or top middle to X and so on. That was a bit of a simplification. What you would really be doing is passing in an updated data model into that binary field. But it was simplified a little bit for the sake of the presentation. But yeah, you can absolutely update even a single attribute on a given item if you wish.
Yeah, I think the point to make there is the payload will still be the full item, even if you're updating one attribute. And small items move at high speed, and so the whole a central philosophy of high-scale databases is that you move the payloads are minimal, and so it's always good to maintain the smallest possible item footprint, even if you have many more rows. Effectively, it's much better to have small items and many more rows than fewer items and that are very large, because you can't break that down when you need to move payloads around. It makes it very inefficient just for general scalability. So one more question on primary key. Does it apply to single attributes, only one hash, one range per attribute, or can you have concatenated multiple attributes represented in either of those?
Yes and no. You can construct data models, and actually we're going to go through a few examples of when and why you would want to do this, where you're essentially concatenating 2 different kinds of information to create a single key, whether it's a hash key or a range key. What you can't actually do is combine multiple attributes, actual attributes, into more than one hash and range key. The hash key and the range key have to be a single attribute on their own, but there are certainly circumstances where you would want to combine different kinds of information into either the range key or the hash key. And actually, we're going to go through some of those examples.
Great. Thanks.
All right. So the next section we're going to talk about is actually adding some social gaming on top of our growing gaming platform. So this is a relatively common feature and something that actually happens quite a bit, and I'm sure there are other examples where you can envision where this is not directly related to gaming, but the idea of building on relationships. So for our purposes, what we would like in our social game is to be able to host games, be able to invite friends to play, be able to find friends' games that are available to play, and see a portion of somebody's history of games. So let's look at what the data model might be for this. So we've changed this somewhat. Now the hash key is the user ID, and the game ID is now the range key. And so in this way, we can have users hosting multiple versions or multiple games over time. So it's not a unique. The game is no longer unique. It's unique across the user. So in this case, what have we accomplished if this is our data model? Well, we can host games, so you can create a new row. You can say, well, now Alice is hosting a new game, so we can do that. And we can bring Bob to play Alice, so we can cover that with our existing data model. What is not as clear is finding friends' games to play or seeing a history of the game. So let's take that second one first. Let's look at what it would look like to look at recent games. So let's say we wanted to say only find the most recent games that Alice has played. So in this case, we're going to query, use the query like we did in the last example. We're going to query against Alice. We're just going to find all the recent games that she played. The problem is that our range key here is a game ID. It's not a time frame. The date is a time frame, but it's not a range key, so we can't query against that. So really what we have to do is get all the games Alice has played and then process it in our application. So this is going to be a costly exercise, and so I just want to take a second to discuss the idea of cost in DynamoDB. So there are two aspects to this. One is the provision throughput, and the provision throughput on DynamoDB is the amount of work per second you are allowed and you have provisioned to your table at any given moment. It is a number you can change, it's a number you can increase and decrease, but at any given moment you have a certain amount of provision throughput on your table. The capacity units are the amount of provision throughput you consume by a particular operation, whether it's a query, whether it's a read, whether it's an update, whether it's a put. You're consuming some kind of capacity when you do that. So this is the cost of a query. It's the cost of any operation. But let's look at the query cost right now. So let's say instead of 3 games, Alice has played 400 games. And each item, each one of these rows is about 600 bytes. Let's say it's exactly 600 bytes. What would it take for us to find the 10 most recent games? So in our case, we can't go by time. We have to get all the games, and then we're going to process it in our application. So we have to do a query for all 400 games. And so if we look at the actual cost, how it breaks down, we're doing 400 by 600. So 400 items, 600 bytes per item. We're going to divide by the number of bytes per kilobyte, and you get 4 kilobytes for every read capacity unit. That means to read 400 games, it costs 60 read capacity units. Now maybe for some use cases that's an acceptable query cost. But the problem with this query cost is that as Alice plays more games, and we hope that our system is very popular, our game is very popular, and they play more and more games. As more games are played, this cost increases. And so it's not really a scalable solution. What we really want, if we only want the 10 most recent games that Alice has played, we want a consistent cost to our games, no matter how, or to our query, no matter how many games Alice has played. And so what we need to do is create a different index on this table. And we do that by using a local secondary index. A local secondary index is really just an alternative range key on a particular table for that hash. So if our hash key is user ID, game ID is our range key, we can create a local secondary index on the date. This gives us the queryability that we really want. And so now, if we want to get the most recent 10 games, then our query is only going to be for 10 items, which is exactly what we want to do. And no matter how many games Alice has played, we're always going to get 10 items. So if we look at the cost for this query, we're doing 10 items by 600 bytes per item, divide by bytes per K, and then divide by K per read capacity units. That ends up being 2 read capacity units, significantly less, and we know it's going to be consistent no matter how many games Alice has played. There are a couple of other examples of where a local secondary index might be really handy. If we wanted, for example, to find out not the 10 most recent matches Alice has played, but against a particular opponent, we could create a local secondary index where the range key is actually the opponent ID plus the date. And this goes back to what I was saying earlier, where you combine certain bits of information to create a range key. And this is a really good use case. So within the hash, it's going to sort its range keys. And so it's going to sort this local secondary index by opponent. And so you'll be able to sort by, it'll be sorted by Alice versus Bob, and Alice versus Chuck, and Alice versus Sally, or whomever. And then within all of those, because again we're sorting, we're going to sort by the date. And so what you can do is do a starts with, and you can do a starts with Bob and limit 10, however many. And so you can find the 10 most recent games that Alice and Bob have played against each other. Another example would be to find a way to explore how many or what games are being hosted that don't have a current opponent. So what we could do in this case is actually have a sparse index, where not every item is going to have this index. We're going to say an unmatched date. This is the date where it was created and it exists unmatched. When you need to find that there are unmatched games, you simply query against this range. And so if it exists, that means that there's no opponent currently for that game. And so it's an easy way for us to find games that have no current opponent. One other thing I'd like to talk about with local secondary indexes are the idea of projections. Projections are attributes on the item that you want to be included with the local secondary index when you make queries. So you don't necessarily have to get the entire item when you make that local secondary index. You don't have to include that as part of the local secondary index. What we say is that you select certain attributes that you're going to project into that index. And the options are, you can say all of them, you can specify which ones you want, or you could just say the keys. The goal here is that you don't want to query anything more than you need to. And so you can make a cheaper query if you only project certain attributes that are necessary for your query. So if you don't really need all the information in the query that you're making against the local secondary index, only project the ones that you do. Interestingly, this actually also makes writes to your item cheaper as well. Let's look into why that is. Because with a local secondary index, there's actually additional write unit costs associated. So if you're creating a new item, you're actually incurring an additional write. If you're setting a range key to or from null, another write. Updating an attribute that's been projected is another write. A non-projected attribute is not an additional write. So that's important. That's another way of saving costs. And finally, if you update the index range key, it's actually 2 additional writes, because to do that, we're actually making a delete and a write. So if we look at this again, we have query Alice's 10 most recent games, or 10 most recent games. Do we really need all the items? Do we really need all the attributes on each item? Or can we get away with fewer? So if we look at, say, reducing the size of the query to being just the user ID, the game ID, and the date. Those things are we need. We want the opponent, and maybe we just want the winner. Instead of getting the entire game state, which compromises the final game board, maybe we don't care about that. And whatever other information that we're including on the item, we're going from 600 bytes down to 40 bytes. This is even less information, even less capacity that we're consuming with each query, because we're only getting the information we absolutely need. And so this is also lowering the cost of making a write, because this way, when we make a state transition, we actually don't incur a cost because we're not projecting the state as well. So this is all lowering the cost of using this local secondary index while providing us an additional way to be able to query our information in ways that we find useful. Any questions?
Yeah, a couple. Can you, I think we're using the terms capacity and throughput, and I'm not sure that we're being super clear on the fact that we're talking about the same thing. Can you just explain, like, let's say read capacity is an example, reads per second. You know, what does that mean in terms of things like the 1 megabyte limit on a return set, the 4K limit on a read unit, and things like that?
Sure. So again, one of the design goals for DynamoDB was for it to be predictable. We wanted to make sure when you were using DynamoDB, when you were using a DynamoDB table, that you knew exactly what kind of capacity you were getting, and you could design your workloads around that. And so we introduced the concept of provision throughput with DynamoDB. And so when you create a table, you set your throughput, the provision throughput, to whatever level you need. You provision a certain amount of capacity units per second, reads and writes, and independent of each other. And so you could have 1,000 writes with 10 reads, or whatever you want. And so that is the level of performance that DynamoDB will deliver to you. We're saying that that amount of capacity is available to you for that moment when you've provisioned it. So if you provision 100 read units, that's giving you 100 read capacity units per second. And a read unit is either it's 4K for a read, and it's 1K for a write. And so the reason why we're saying units is because the amount of information you could read or write at a given moment could be vary dramatically. And so writing 10K is different than writing 1K. And so that's why it's a unit rather than the number of writes per second you can actually make. And so when I talk about making provision or creating provision throughput, using provision throughput, this is what I'm talking about. The amount of throughput that you have requested on your table that DynamoDB is providing you. The capacity are those read units or those write units. And so when you make a read, you're reading a certain number of units because you're saying, well, I need to read X information off of my table. That's going to combine to be, let's say, 20K. That's going to be divided in by 4. And so we're going to say consume 5 read capacity units. As long as that's less than the amount of capacity I've provisioned for my table, DynamoDB will go ahead and service that request. Rather than if it exceeds what we've provisioned, then it's going to say, you're gone over your capacity. This is an error. There are some limitations, as David implied. There is a limit to how much data can be returned at any given moment. So if your read exceeds 1 megabyte, then we're not going to be able to return all that information at once, and instead the read is actually going to be, for all intents and purposes, paginated. So DynamoDB will return the last key that it was included with the payload that it returned, and so you can keep on doing additional queries to get the full amount of information that you want, if you want more.
Great. And let's talk a little bit about the indexes as well. So can you talk about their impact on storage and capacity? I know you went through that on the slide just briefly, but I think it's important to understand as a primitive state. This happens underneath databases everywhere. We just make it a little more visible in DynamoDB. Exactly what the implications are on storage for having an index or 5, and the same sort of thing with throughput.
Sure. So with the local secondary index, there are some limitations, as David implied, to having only a certain amount of data being able to be stored on that particular hash. And so you're then, if you create a local secondary index, you're limited to 10 gigs of data stored on per hash. And so that's simply because David said we're doing additional things underneath the hoods that has become a little more visible to the end user. And so that is definitely a cost and performance implication that you need to consider when using local secondary indexes, and that comes down to a cost versus benefit as necessary for your application. In terms of the attributes and the writes that you're making in the throughput, it's still all part of the same table, and so the throughput that you're consuming is still part of the overall table throughput that you've provisioned. But there are additional costs because we're making additional writes, additional reads behind the scenes in order to maintain that index. And so that's where I went through that chart of where the additional reads and writes or the additional writes are when you're updating items that include a local secondary index. And so because there's additional work that DynamoDB has to do on the back end, there's additional costs associated with maintaining that index.
Exactly. Yeah. So and I think an important concept too is sparse indexes. So if you have an index on an attribute that doesn't exist, there is no cost at all in terms of storage or throughput. As soon as that attribute exists, then that index will be populated. So there was a write to that index for an insert. There's actually 2 writes for an update, in that indexes are always managed as a delete plus an insert. But of course that enables a query pattern against that index where obviously for the cost of a read unit, you can read exactly the data in exactly the format you want. And that's the point of indexes in all databases. And so to be clear on that, you can read against the hash key, against the range key. You can query against the range key. With local secondary or even global secondary indexes, which we also have, you're designating alternate range keys for a local secondary, and so you can query against that. In a global secondary, you're designating alternate hash keys and or alternate range keys, and of course you can select and query against those as well. So yeah, the whole idea of indexes, as it is in any database, is to increase the query flexibility that you have against the system. So yeah, it's all about the read patterns and making them super flexible. And of course, as indexes, they're automatically maintained, so you don't have to build them and maintain them yourself. Okay, let's keep going, and I'll bring up some more questions at the end.
Sure. So we're going to add on to this social gaming platform that we've created by being able to introduce the concept of relationships. So building in relationships, probably key to a social network, but also key to a lot of different kind of transactional systems where you want relationships between different entities. And so how we're going to do this is by using or introducing transactions into DynamoDB. And before we do, I'd like to just set the table a little bit and introduce a caveat. In DynamoDB, all writes are atomic and reads are isolated for single items, but not cross items. And so what we're going to do is actually introduce some ways where we can build on those atomic features for some higher level transactions. But you really need to keep this limitation in mind when building or designing a data store for an application. There are lots of circumstances where DynamoDB makes a really good data store, but not every single one. And so understanding and knowing where the strengths and limitations are really important to being able to use DynamoDB effectively. And so this is kind of one thing where there are aspects of DynamoDB that aren't implemented that can be implemented by certain best practices on top of that, but you need to be aware of that. Secondly, the caveat is that while transactions have uses and are sometimes necessary, there is an additional expense to using. There's an additional cost to that, and so you really need to be aware of it, and that it's really best used when you need it rather than you want it. So back to what we want to build here. Now what we want to do is add the concept of friendship or creating friend relationships within our application. So we're going to say we want to be able to say, who are my friends, be able to send out friend requests and reject or decline friend requests that come to me. Pretty basic. So now what we have is a friends table. We have mutual friendship between Alice and Bob. So we're saying that in order for a relationship to be acknowledged as done, it has to be a two-way street. So Alice and Bob have to be friends as well as Bob and Alice. In this case, we're saying that Chuck has sent Bob a friend request and Bob has got it incoming. So this is our current state. So if we look at it from Bob's point of view, hey, I've got an incoming friend request from Chuck. And so now what happens if Bob says, yeah, you know what, Chuck and I are friends, I'm going to accept that. And so what we really need to do, because again, it's a two-way street, is update both records. So we're going to update Bob and Chuck, and then we're going to update Chuck and Bob. And so we say, Bob, update items, now we're friends. Okay, great. And then a second transaction is going to be update Chuck and Bob to be friends. Done. However, what happens if something goes wrong? You know, at the end of the day, there's as much of a virtualized platform as it is underneath the hood. There's hardware down there, there's networking, there's people using cell phones that get drop signals, laptops that don't work, browser sessions that end unexpectedly. Whatever reason, at any point along the path of Bob saying accept to it finally being written to DynamoDB, there are a million things that could go wrong and the request could go awry. So let's say in our case, Bob has said, yeah, I'm going to accept that friend request. We got to update both records. So we're going to update the Bob-Chuck record to be friends, and we're going to try to update Chuck and Bob, and at some point something went wrong. The request never went through, so the change never happened. And so what do we do in this case? This is a multi-step write action that we want to happen in conjunction. And so this is the case where we start looking at how do we implement transactions. And so there are a couple ways we could go through this. We're going to talk about a few of them. What you could do is actually scan your table for transactions that don't make sense given where they are in your table. You could use the client-land transaction library, which is part of the official AWS SDK for Java. We'll talk about that. Or you could roll your own scheme. You could figure out your own way of dealing with transactions in your application. So let's look at the first one. One thing that's very helpful if you're building an application that maintains differing kinds of states for, say, relationships or anything, is to build a replayable state machine. And so if we were to do this for the friendship relationship in our application, what we could do is look at the different states that we think are acceptable. So when Chuck initiates, he's going to say sending. He can write that. And then Bob is going to, once that comes in, Bob can update his state to say incoming and then set Chuck and Bob to be sent. And this is a complete state. This means that all this means, incoming on the Bob-Chuck side and sent on the Chuck-Bob side, means that Bob is sitting on the request. He hasn't decided to do anything, and that's an acceptable end state for both of them. if we're not going to deal with denials, but it's relatively similar conceptually. If Bob says he's going to accept it, he's going to update his state to be accepting, and then Chuck and Bob get to friends, and then finally Bob and Chuck get to friends. So that means that the two friend states, when they're both friends, that's an acceptable end state as well. Where we start looking for incomplete transactions is where something's in accepting, something's in friends, and that's not a acceptable final end state. Or sending and incoming, that's not an acceptable final end state. And so you could easily conceive of a scanner, some sort of sweeper program that goes through your table and checks out the state and then updates the state where it's in an impossible final state, where it needs to be updated to some level. Now, we could also look at the transaction library for Java. And so, like I said, this is part of our official SDK for Java. And what this does, it actually builds on two additional tables that you need to create. It creates a transaction table to grab transactions in flight, and transaction images table to grab the state of an item before it's been updated. Interesting, or things to know about for the client transaction library. It's really ideally best suited for low contention tables and items. It's not really best suited for high volume items because of the additional rights that you're going to be making to ensure that the transactions proceed. Mixing regular rights with transactional rights on a table is a really bad idea. It's going to mess up how the transactions go, and you'll probably end up having the transaction library making changes that you don't expect if you mix and match. You can't query the transaction library tables. And then finally, like I said, because you're using additional tables, because you're making additional reads and writes, it's going to be more expensive. There are extra steps. It's going to be slower. However, all that being said, it does make transactions much, much easier. It's all built into the SDK as you use it, so it's actually very, very easy to use. So if it's necessary, it's very handy. Let's look at what it actually looks like. And what we'll just be doing is looking at the transactions table because the images table just grabs an image of the item before it gets updated. So in this case, Bob has said, yes, I'm going to accept the friend request from Chuck. So instead of doing writes immediately, actually what we're going to do is do a get. We're going to do a batch get on the particular items in question, and we're going to write them to the transaction table. And in this case, we're actually going to use Bob and Chuck as a combined hash key. And again, this is one of those circumstances where I said you want to combine information into a single key that may come from different attributes, but still a single attribute. This means that if we were to make any other transactions on Bob Chuck, we would already have this in here. And so we're essentially locking those items down. Additionally, when we put the item in the transaction table, we're going to expect that it doesn't exist. If it already exists, that means there's a transaction already in flight about this. Again, we're going to reject that transaction because we don't want to overwrite something that's already there. The other thing I want you to notice is that we're actually putting in versions of the item. When you can see that on the existing table and in the transaction table. And this is so that we can track what level of the transaction we're at, and so that we ensure that we're not overwriting future transactions because we're going to know what version we're at, what version we're going to. So now we've written to the transaction table, and we're going to apply the rights. We're going to say, yes, update Chuck and Bob to be friends and increment their version. And then we're going to say the transaction's done, delete the transaction. So again, and this is again done with an expected version. So we're not deleting the wrong transaction, something else that may be in flight and so on. We're making sure that we're always looking at what's expected and verifying that that's expected and only proceeding after that. So again, what happens if something's gone wrong? Something exploded, the network, whatever happened, something happened. So same procedure, we're going to do the get first. We're going to get the two items that we want to write to. We're going to write to the transaction table. We're going to write the same information. And then we're going to try to update Bob and Chuck. That worked. And then we're going to try to update Chuck and Bob, and that didn't work. Something happened. Who knows? And then so now we bring in our sweeper. And what does the sweeper do? The sweeper actually has a much easier job in this case than it did in the state machine, where the state machine sweeper had to go through your existing friend table and check for the status of everyone, compare against other things. The sweeper in this case only checks the transaction table. If there's something on the transaction table, that means there's an existing transaction in flight. Did it finish? Who knows? All we're going to do is just take what the transaction tells us to do and proceed and try to do the update and then delete. So, well, we're expecting Bob and Chuck to become friends. Let's try to update that. if we try to write to Bob and Chuck, the expected version is already there where we're expecting the previous one, so that write's going to fail, and that's fine. Chuck and Bob, the expected does equal the previous version. It was version 2. Now we're going to change it to version 3, update the version to friends, and we're done. And then we go ahead and delete that transaction. And again, you can see that even if, let's say, this last step failed, if this delete from the transaction table failed, the sweeper will go through, try that same thing. Both writes will fail this time based on the conditions, like they should, and then it'll go ahead and delete the transaction. So the sweeper has a much simpler time being able to determine what transactions have completed and what haven't. So again, even with all the additional costs being borne in mind, it does have a much easier job, and it's an easier implementation. A few words of advice about transactions, and these are really kind of best practices in general about transactions, is lock items. Make sure you lock items so that you can only have one transaction at a time. And this includes anything that you're creating, anything that's new. You don't want to be modifying the same kind of data at the same time from two different logical locations. Use versioning to make sure that you're not overwriting what you're doing in the future. Sweep for anything that's stuck, and avoid deadlock. One of the best ways to avoid deadlock is to make sure that anytime you write to multiple locations, you write to them in the same order so that the locks come in the same order. So the individual transactions have to wait for other transactions to finish completely, rather than having, say, transaction 1 grabbing, say, table A, transaction 2 grabbing table B, locking them, and then waiting for each other to finish. That's a deadlock condition that's never going to finish. So these are general transaction best practices, things to bear in mind, but they also apply to using the transaction library on DynamoDB. Any questions?
Yeah, great. We have we have quite a few. One question: if we have a lot of tables, and this really goes back to how do you divide your data? Do you have a lot of tables, or do you have a lot of items in one table? So, assuming you have a lot of data that is separable, let's say shardable, how would you implement that ideally in DynamoDB?
I think it really depends on a lot of factors. I think one thing to bear in mind is if the fewer tables that you have, the less amount of overall provision throughput you're going to consume. If you need equal access to all those items, the more you spread out your tables, say you need 100 reads and writes per table. If you've got one table, that's only 100. If you've got 5 tables, that's 500 reads and writes. So there's that. But it really kind of depends on why you would want to spread out your information. There are certainly circumstances where you could see why you would want to do that. If you need to shard geographically, let's say you have, in that case, you could do a Dynamo table in the States, one in Europe, and one in Asia, and that makes sense. But it really kind of depends on why you would want to do it. For my point of view, if I don't need to do it, I wouldn't do it because I find it easier to interact with one table at a time than 2 or more. If I don't have to, I'd rather leave it to 1.
Good question, good answer. And I think the point about that is also that very large tables are not a problem. DynamoDB was designed for that. So if and that's the whole principle behind the hash key. That the hash is your shard key effectively. So having very high cardinality hash keys is essential to good distribution. Even if you're using range keys, having a few hash keys and a lot of range keys is going to give you hotspots unless you're very, very careful about your workload. So yeah, the best practices apply for hash key selection. Quick question. So in the example you described, you talk about sweeping and putting a background sweeper. Does that sweep occur automatically, or is that something that has to be built and scheduled to run periodically?
That's definitely something you need to build and schedule inside your application so that you know that your transactions are completing.
Got it. Okay, great. We'll move on again. Thanks.
Great. So our next module is a bit of a departure from our game, actually. It's not going to directly tie into our game, but it's something that we wanted to bring up, and the concept of write sharding. And the example we're going to use is for really high throughput voting, very high capacity voting. So the scenario is you've got an individual voter making some kind of vote to an application that ultimately writes to DynamoDB, which is storing the number of votes for however many candidates. Let's say we've got 2 candidates. The write essentially comes in, and what we're going to do is actually use an add as part of the update item. If you use an add on a numerical attribute, it will actually increment the attribute itself. And so you can actually, this is a great way of capturing votes. And so in this case, we're going to do an atomic increment on the vote for candidate A. That's all fairly straightforward. This particular pattern, very straightforward. But like I said earlier, we want to make sure that we're designing for scale. And the question is, have we designed for scale in this particular case? And so we've got an election coming up. And so we're going to design for scale on our DynamoDB table. We're going to provision 1,200 write units. On the back end, DynamoDB is physical hardware. It's virtualized from your point of view, obviously, but at some point, obviously, there's something physical where data is being written to. And so for this case, let's say, for example, your 1,200 write capacity units ends up being 2 physical partitions provisioned by DynamoDB on the back end. What happens, however many partitions actually happen, this is true of whatever you've done, the different partitions each get an equal share of your capacity that you have provisioned, and they do not share it. And that is very important. And so each of these 2 partitions, in this particular case, they're going to get 600, and they're not going to share it. So the capacity of each of those partitions is just 600. Now let's say we've got a really big election coming up. We're going to say, you know what, we're going to have a ton of people writing. We're going to have 200,000 write capacity units on this table, which means everywhere from partition 1 down to partition n, we've got 600 read capacity units each, and they are not going to share. Now, given our hash key, we've got 1 hash key for candidate A, 1 hash key for candidate B, and let's say we're trying to capture the federal election where we've got 2 very major candidates and a handful of candidates that, you know, comparatively get very, very small numbers of votes. In this case, we're going to overwhelmingly write to candidate A and candidate B. So in this case, we're going to try to write about 70,000 writes per second to candidate A, 50,000 writes per second to candidate B. It's not going to work. You're exceeding the capacity on a particular partition. DynamoDB will return errors well before you get into this range of numbers. So what we have to do is figure out a way to be able to efficiently use the capacity that we've provisioned, as well as efficiently use the partitions that DynamoDB is capable of doing. It's got to be able to handle the hardware at some point. It can't just magically create hardware that handles any kind of workload. We still have to deal with the fact that at the end of the day, these are physical devices that you need to be able to deal with. So going to our developer guide, the DynamoDB developer guide, what we really want to do, this is the thing that David was just talking about, is we want to spread our load evenly across different hash values. And so how do we do that if we have 2 candidates that are overwhelmingly consuming most of our capacity? Well, in this case, what we're going to do is actually spread out the candidates equally among different hash keys. And so what we're going to do in this case, we're going to do a random number between 1 and 9 or 1 and 100, 1 and 1,000, whatever that may be, as well, so that we can get an even spread of hash keys across our DynamoDB table. And so in this case, instead of candidate 1 being on a particular partition, candidate 2 being on another partition, they're actually spread across multiple partitions. And when we make an update to capture a vote, we're just saying we're going to write to random locations. As long as it's candidate A, we don't care which partition it's hitting. And then periodically what we can do is do a sum of all of those votes and just store them on a particular table where we have the total vote count. And so in this case, we're actually spreading our writes out all across the partitions, and we're not over exceeding capacity on a particular partition. Let's say we have the same idea going but for reads, and we want to make 70,000 reads on a particular partition, 50,000 on another. And right now what we're doing is reading the totals. Let's say the election's over and we've got all sorts of people who want to find out what the totals are. We're exceeding the read capacity on these particular partitions. Same idea. We're going to exceed that capacity. DynamoDB is not going to let that happen. And so this particular design pattern is actually very similar to any kind of design pattern you've seen for a relational database. Let's cache the results. The results aren't going to change. Let's put a cache there, hit the cache first. We're significantly lowering our read throughput, or our capacity consumed on those particular partitions for reads. Any questions on that section?
No, we're actually out of time, so we're going to wrap it up there. And by the way, we do have all your feedback. There's a lot of questions we didn't get to, but thank you, Peter, Mark. One thing we're going to do is put a quick poll up. If you could just respond to the next couple of slides, that'd be great. We do rely on this information to determine what we present, what subjects you're interested in covering. Design is always a popular one, hence this session, and we are planning more of these. So with that, I'm going to let you go. Thank you, Peter Mark, for your time, and thank you everyone for joining.
Thank you, everyone.